So this today webinar is talking about the topic of oil-free compressed air and the definition of oil, the possible treatment systems, and system solutions. And yeah, as Patrick already mentioned, you are able to put your questions in the chat room or in the chat window, and we will have several breaks in between according to the agenda that will appear also in between that. You will see on what stage we at the presentation. So how does the agenda look like? So at first we will shortly have a look on some applications and the required quality classes, particularly in terms of the oil content. On the next step is the question, how does the oil get into compressed air? We will have a closer look on the oil itself, so the molecular structure, so a bit of chemicals, but not too much. And then we will see how compressors will influence the oil content in the compressed air system. And what about to think about the suction conditions? One next point will be how do I get the compressed air oil free? And this is the longest part of this webinar session. We will see the possible processes, their positive and negative points, and we will also compare the oil-free compressors with lubricated compressors, including the treatment system. And finally, we want to be sure, or the customer definitely wants to be sure, and that's the reason why we also integrate some kind of measurement technology into this webinar, and we'll have a closer look how to equip a compressed air station with the relevant measurement technology. So that's so far the agenda, and as I said, in between we will have the breaks where we will come back to your questions. All right, so let's start with the first point, the applications and the recommended quality classes. Here you can see one easy example. So that's a robust application in a heavy industrial area, and one other tool that also consumes compressed air looks a bit different. And quite obvious is that the difference between both is the demand not only in airflow. Definitely there is a difference in the demand of quality, but in both cases these applications using compressed air to drive tools. So the more sensitive application here at the dentist that links me to a few further applications which appear in the industry, or let's say what industry in general are consuming compressed air in a high quality demand. So there we have several industries as example. So the pharmaceutical, food and beverage, packaging industry, as well as medical laboratories and chemical industries. And here on the lower left bottom area here, you can see that there is also an application mentioned. This is not directly related to a kind of industry, although obviously there's a car here which is painted somehow, but sensitive applications may appear in different industries, and not the whole industry or not the whole factory requires the same quality of air, but a certain type of application. So you generally could say when the products are somehow produced with compressed air, they require a certain kind of quality class on a high level. And this is particularly true for the oil content. So what about the quality classes itself? The quality classes in terms of oil probably are for the same application may vary. As I said already, that depends on the industry, but it also depends on company regulations. So there are many, let's say, recommendations from companies, from industries, from a quality management system who decide what's the best for my application, but where to find the answer, that's the point. And even the institutions such as VDMA, BCASE or KGI, they recommend different quality classes in terms of particles and water. But luckily, they mostly agree in terms of the quality class of oil. Then you may have also realized that there is quality class 0 mentioned here in terms of oil. And what about that? So in my opinion, there's a myriad of class 0. It's mostly a perfect marketing communication, but it also but tells you nothing, yeah, in fact. Because the class 1 already defines the amount of oil to be equal or lower than 0.001 milligram per cubic meter. So in fact, there is no reason to communicate any value which is classified in the class 0. And anybody in the compressed air should be very careful to communicate or agree alarm values which are lower than 0.01 milligram per cubic meter. You may all know that a compressed air station or system is a quite flexible and quite dynamic operating system. And we often run the risk of peak loads, of peak values in between. And once you have a quite low setting of alarm values, these peak values may trigger an alarm, and that may shut off the valves, and so finally there is no airflow for the application. This is particularly true if there is no automatic bypass or redundancy installed. So my recommendation is to be careful with alarm settings in low values, and if there is an alarm required, the delay time until the alarm should trigger some activators that should also be considered. So where to find now all the answers to these questions? These are not in the industry itself, but they are more in the application. And on the way to the application, there are different scenarios. Yeah, the location of the pipe system, for example, this is related to systems which are installed indoor or outdoor. So that means there's a different kind of pre-drying required. And the question is the same quality of air required for the whole factory? And that leads to the question, is a central treatment system or a point of use treatment economical and or more efficient? Another point is the internal quality management system of each company, because mostly the customer itself or his quality management system classifies the application in terms of the contact with compressed air. This is particularly true for the food industry, which decide whether that is indirect or direct contact of compressed air. And generally, if the products which are manufactured has the contact with compressed air anyhow. So this is a bit related to the point above, but also dependent on the situation on site. So imagine you have your customer has a factory with several buildings, but only in one building is a compressor station. So we all may think about what is most reasonable to treat the compressed air. Is it either centralized at the compressor station, or is it better to treat the compressed air locally at the point of use where the better quality is required? To sum up this, it mostly comes up to two different quality classes. And here you see that there is the 1-to-1 quality class or the 1-for-1 quality class. The major difference is in the oil vapor content. And for example, these institutions such as VDMA or BKs, they recommend these certain quality classes in terms of water vapor, depending if the application has direct contact with compressed air or an indirect contact. And additionally, the number in brackets here, they differ from the others in terms of particle quality class. So the reason is that in terms we have a sterile application process, the recommendation is that we treat down to quality class 1 in terms of particles. I guess the reason is that particles are a base to carry bacteria and germs into the system. So the lower the level of particles is, the lower is the risk of carrying bacteria and germs into the system. Finally, another point is that still mentioned the question, does the whole factory require oil-free air or not? So that's so far the questions about quality classes and what are the applications that comes into play here. So far, I guess there are almost no questions, but I will give the chance if there was popping up some in the chat room. What about that, Patrick?
No, you're completely right, Bernd. There are no questions so far, so you can go on if you like.
Yeah, thanks very much. That was just a soft content so far. So now we go a bit deeper into the topics here. The definition of oil, compressor, and their influence and the suction conditions. So what about the oil itself? So the oil is a kind of chemical structure. And you may see here the basic of this chemical structure, which includes some C atoms, that means some carbon atoms, and some hydrogen atoms, and all of these are combined in a molecular structure. And the minimum number of C or of carbon atoms is to be named as 6 carbon atoms. This is the minimum number to be classified as oil according to the ISO 8573-1. That means once I have hydrocarbon molecules with shorter chains with less C atoms, these are not integrated into the ISO standard, but they may have an influence on your production. The shorter molecules mainly occur in the pollutions from the ambient, which are aromatics from flowers or trees, for example. And the longer chains are to be used to build more liquid and more pasty or more solid components of hydrocarbons. They all have longer chains of hydrocarbons. Yeah, so how does a lubricant for compressor looks like? Because that is one of the most important hydrocarbons we need to consider. That is quite different. An example of one compressor oil you will see on the table, which pops up in a few seconds. And this table demonstrates that oil is not only one hydrocarbon molecule, but it always is a mixture of various hydrocarbons. And there are quite a lot here. And so this is, you can say this is a recipe of one lubricant, of one type of lubricant, and the summary of the percentages is 100%. So that's the overall ingredients of one lubricant. And these ingredients, or these hydrocarbon molecules, they differ in the ability to be adsorbed, for example. This is particularly important for activated carbon towers because the performance of these carbon towers depends on the type of oil vapor that enters the system. We will come back to that topic also in a few slides later. So this is here a typical example for a regular type of oil, for a regular lubricant. But what about the others? So there's also a kind of food-grade oil. And you could say there's somehow a mystery. We quite often face that story about the food-grade oils. And I can imagine there are a lot of stories people tell about that. And what kind of food-grade oils can only be used as a lubricant? And there's only one, which is the H1. This is only possible, and this is only accepted as a compressor lubricant. Furthermore, the allowed contact with food is also limited. This is indicated here. So even if this this oil is named as a food-grade oil, the allowed contact is just incidental. So it's not allowed that this oil comes into continuous contact with some food application. That's definitely one point that must be considered. And you can easily imagine once the brand new oil has passed the compressor, the structure of this oil is totally different. And so many components has added to this oil that there's a high risk of contamination with some food application. I would say at the end, this is also a kind of good marketing that the oil industry discovers or develop this kind of oil, which costs the customer a lot of invest and of maintenance costs, because usually the oil consumption of the compressor is a bit higher when that runs with food grade oil. So the amount of oil that needs to be exchanged is higher than the amount of a regular lubricant. All right, so that's so much about the oil issue. So what about the compressors? Because also the compressors have an impact on the oil carryover into the system. We will have a look on four quite common examples here. So the one is the piston compressor. That's quite simple setup, but it's very efficient, and it's available in both versions, in lubricated and in oil-free. Then you may find a vane type compressor. In my experience, it's a quite seldom type of compressor in the compressed air business. And as far as I know, this is only available in the lubricated version. But please correct me if I'm wrong. You can just give an answer in the chat room. The next type is the screw compressor. This is very popular, although the efficient is not as good as the piston type of compressor, and this is particularly true for the oil-free versions. And related to oil-free versions, the last type of compressor is the centrifugal compressor. This is typical for bigger airflow applications with a lower system pressure. And this type of compressor always compresses oil-free. So there's no lubricant in the compression chamber. So what is now the influence, or what is the oil carryover into the system? That is displayed on the next table that will appear, and the numbers of this table are based on the experience from the VDMA. So here you can see that we have a quite different amount of oil carryover. For example, here the piston compressor has up to 180 milligrams per cubic meter, and compared to the screw compressor, would have just 20 milligrams per cubic meter. So in fact, the piston compressor has an almost 10 times higher oil carryover into the compressed air system than the screw compressor. And yeah, the column on the right is just to give you a feeling in case you have a 24/7 load time per day, you have that amount of oil carryover into your compressed air system. That means that also is the amount of oil that will be loose, but that will the compressor lose. So in a couple of days, you need to put in some more new oil in the compressor. So what else is responsible for the oil carryover from the compressor into the system? There are a couple of further impacts more. One is, for example, the interval and the quality of maintenance. That is, of course, important, that quality of maintenance is on a high level, and the intervals follow the recommendation from the manufacturer of the compressor. Then one impact is the relation between load and idle phase. Particularly in compressor station where multiple compressors are installed, the controller of these compressors needs to be programmed in a good setting. Otherwise, some of these compressors are in a long idle phase, for example. And in some cases where customer just have one compressor installed and has the VSD type for what reason ever, in many cases, this VSD type also runs for too long time in idle phase, and that also have a negative impact on the oil carryover. Beside the compressor itself, the location is very important. So what's the ventilation of the compressor room. If there's poor ventilation, it has a negative impact on the temperature of all components. And that guides also to the compression end temperature. If there's a worse ventilation, it has a problem of suction pressure. That is one point. So the performance of the compressor will get lower, or the energy consumption will increase. But if there's a poor ventilation, I also have an increase of the end temperature. And the higher the compression end temperature is, the higher is the oil vapor which is created in the compression room, and the oil vapor is being carried into the compressed air system without any reduction, because the oil separator in a screw compressor, for example, only reduces or only separates the aerosols from the airstream, but not the oil vapor. Furthermore, the lifetime and the type of oil is one influence. Type of oil is that mineral oil and synthetic oil has different vaporization temperatures. So mineral oil vaporizes more easy compared to synthetic oil. And also the lifetime is important because the function of the additives is that critical point here. Once the lifetime of a certain oil is exceeded, so when the maintenance interval is exceeded, the function of the additives will get dramatically worse. So they will lose their properties quite shortly. That means the foam generation will increase, and once the foam generation will increase, also the amount of vapor will be increased. Yeah, last but not least, suction conditions are an important factor that has an impact on the oil carryover into the system. So how does suction conditions look like? So we have several examples here, some from traffic, industry, and some nature areas, and all of these carries particles and aerosols into the system. And on each particle and each aerosol, somehow oil droplets or oil vapor is being carried into the compressor, or sucked into the compressor and being carried into the compressed air system. And as already mentioned, of course, from the compressor itself, even if these type of compressors are running in oil-free compression mode, most of them has a lubricated gearbox. And all these gearbox has a ventilation area. So that means the oil vapor is released to ambient due to the crankshaft ventilation or the gearbox ventilation. And that finally influences the suction conditions. So to come back to the table of the compressors, once we pick up all the compressors in oil-free versions, except the vane type, we still have a certain amount of oil carryover into the system, just because of the suction conditions are already polluted with some kind of oil vapor. There is one institution here in Germany that measures on certain areas the amount of hydrocarbon in ambient, and that's what I would like to show here. That's a federal environmental agency in the middle of Germany, and the source is also mentioned here on the bottom of the slide. So unfortunately, that's only in German. But you can pick up areas where the ambient is measured, and you can also pick up what type of ingredient of the ambient you would like to be displayed on the tables. And the result of these measurings are here visible on the graph. And the location of the measurement was in two different cities. Yeah, that's Ludwigshafen, Trier, and Koblenz. So Koblenz and Trier are cities, or small cities in Germany. They are located on a more countryside area, and Ludwigshafen is a typical industrial area with a harbor area at the River Rhine with big ships and heavy industry, and that automatically displays that this kind of area has a higher pollution of hydrocarbon. So the light blue curve here is from Ludwigshafen. compared to the others, which are on a bit lower level here. But all of them, no matter on what time of the day or what day, all of them has an amount of hydrocarbon which is higher than the limit value of class 1. And that's the reason why, no matter if I have an oil-free compressor integrated into my system, I additionally need somehow oil-free treatment system. And of course, the best would be that one with the BEKO, which has continuously lower residual oil content than that of class 1. All right, so far, that was it about the definition of oil, the compressors, and the suction conditions. So what about questions so far in the chat room?
Yes, Bernd, there's one question, and even though I know that we will get some more information about the BEKO in a few minutes and in a few slides, you already talked about food-grade oil, so maybe we just give a short outlook for the moment. The question is, does BEKO work with all hydrocarbons, also with food-grade oil?
Yeah, that's a good point and a good question. And an easy answer is yes. Yeah, because this chemical reaction, where we'll have a closer look to in a few slides later, the chemical reaction is not influenced by the type of hydrocarbon. This is very different to the adsorption process. And probably that's the reason why that question appears. We also know that from oil-water separation processes that also these have some kind of problems with condensate that is appearing from food-grade oil condensate. And also the adsorption process is negatively influenced. But BEKO for sure has no problem with all kind of hydrocarbon.
Okay, that's already a good answer. But as you talk about it, or as we speak, there is a second question. Does BEKO work with silicon-based lubricants like polyglycol?
Wow, another good question. Honestly, I'm not absolutely sure, but I think I remember that there was no silicon to be detected after BEKO. I'm not absolutely sure, but so far that's some kind of discussion I remember when we talked with the product managers together. I'm not pretty sure, but I think that should be no problem.
As far as I know, we had some talks about this in the past, and as far as I know, the problem is the measurement afterwards. The only thing we know is, of course, or the only thing we can measure, like with our OCV or with whatever measurement method you like, is hydrocarbons. Now, to measure how many silicon-based molecules you have left in the air, there's simply no way to measure this, except taking a sample and putting it to laboratory afterwards, and then this is again months and weeks old, this sample. So as far as I remember, we had some customers who had problems with silicon in their compressed air in the past, and had problems with, for example, it was again car painting industry as far as I remember.
Yes.
And after they installed BEKO, they didn't have these problems anymore. So even though we cannot measure exactly if there are still silicon-based molecules in the air after the BEKO, we only know that some cases from customers that already bought the BEKO showed that they didn't have problems after installing the BEKO that they had before. I think that's what I remember about this topic, but I don't know if we have exact measurement options so far or nowadays.
Yeah, couldn't give a better answer than you gave already, and that's also what I know from the past.
Yeah. Okay, then. Yeah, two different lubricants. Polyglycol is separate. Yeah.
All
okay.
Right.
Then let's go on.
Let's go on. Okay. So now we come to the next point. And the next point is about possible processes. There are positive and negative points for the first step. So what are possible processes to treat compressed air oil-free? At first we have these two ones, which is adsorption with activated carbon and the chemical reaction with the catalytic converter. But not to forget the oil-free compression. And this is extra marked here as compression. Once we mostly communicate about oil-free compressors, this actually means an oil-free compression. So we will start with the oil-free compression itself and what is the positive and negative points here. So on the positive hand, we have, in fact, we have a good reputation. And this good reputation is also a part or a result of good marketing. And of course, in fact, the oil-free compressor eliminates the risk of an oil breakthrough into the system. And one could also say it's probably it's worth to think about why should we put oil into a system which does not allow oil? It's some kind of question that may people think about in the next future of technical development. Another positive point is it follows the industry requirement. But this is also often based on marketing. And it let customers feel safe, because there is no risk of oil breakthrough, but there is still some oil which enters the compressed air system, which we have seen already in the slides before. So it still requires some kind of air treatment system. On the negative side, we have the energy consumption. So why is the energy consumption negative compared to lubricated compressor? The point is that there is no oil. And the oil have, beside cooling and lubrication, it has the job of sealing. And if there's no oil, I have a higher risk of backflow from the pressure side to the suction side. And to eliminate the risk of backflow, I need to have a higher turn speed. And the higher turn speed of the compressor result in a higher energy consumption. So then the invest is one negative point. One reason is that, for example, the bearings of the oil-free compressor are more complex and needs to be in a higher quality. Also, the manufacturing process has to be done with smaller tolerances. So that altogether brings up a higher price for the compressor. Maintenance costs for oil-free compressors are also quite higher than lubricated ones. You may find discussions in the market that compressor manufacturers tells you different numbers because there is no oil that needs to be exchanged. But once the air end of this oil-free compressor will break, it's easily that this is half the price of the compressor or even more that needs to be exchanged. And finally, the air is only as good as the ambient. And this oil-free compressor will never give you class 1 in oil if there's no additional treatment installed. So next point is the adsorption with activated carbon, and in our point, that's the clear point V's. On the positive side, we have the invest. Of course, it's a very cheap setup. It's a very simple construction. So that's the reason why it's quite low in invest. The energy consumption is, of course, a positive point because that equipment does not require any power supply. And also the footprint is a positive argument. It has a small size and a low weight compared to other treatment systems. On the negative hand, we have a couple of more issues. The maintenance costs, for example, due to regular exchange of activated carbon and filters which are required to run the system continuously on a high level. The performance is load dependent. We will see also in some of the next slides that this is particularly true for the airflow, and we already talked about that compressed air systems are running in dynamic mode. So there's almost no constant airflow, and you have sometimes of high flow and low flow. And particularly the low flow is critical here because the low flow automatically results in a low velocity inside the tower. And if the velocity is too low, that's the worst conditions for contact of hydrocarbon with the activated carbon surface. That's the reason, for example, why we recommend a minimum flow rate of 50%. And additionally, the carbon tower or the adsorption process is sensitive against high inlet dew points. We will also pick up that point in a few slides later. So it has also a limited adsorption capacity. That is based to the physical processes and parameters. which will also be described in some of the next slides as well. And there's no process safety, because these towers have no control units. So there's always a risk of some kind of oil which is being carried out of the tower into the application from the customer. Right. At last but not least point, we have the chemical reaction with catalytic converter, in our case the BEKO-CAT, and that has several positive arguments. It's the energy consumption. Some people may wonder why that is the positive point, because it is power supplied. Yes, of course, it is power supplied, but the BEKO-CAT has a high efficient insulation that captures the heat once it is being generated within the system. And the full power of the installed electricity is only required for the preheating phase. During regular operation, it's about 30 to 50% of kilowatt which is being consumed by the BEKO-CAT. Maintenance costs here are also on the positive side, because so far, already by experience, we know that the lifetime of the catalyst is almost endless. In the early years of the BEKO-CAT, which was introduced in the market, we recommended to exchange every 20,000 hours. But by experience from more than 10 years of BEKO-CAT in the industry, we know that lifetime can be extended very easy. We figured out that by measurement, and that is the result. So the time when the catalyst needs to be exchanged is quite long. So in the new generation, we recommend something about 5 years. So that is totally different to a yearly exchange of activated carbon, for example. Another positive point is that this unit is load independent. So no matter what's the temperature, what's the water, what's the oil inlet, these are all parameters the BEKO-CAT doesn't care about. And it's also almost fully independent of the airflow, because the process is supported by heat and catalyst together with oxygen. So this is the reason why this is more or fully independent on fluctuating operating conditions. Our recommendation is that you should not go below 20% of flow load, and this is, in most cases, that is quite easy to handle. It has the highest process safety because the whole process is fully temperature controlled, and that covers all the risks that may appear if you have just an activated carbon tower which is not controlled, but the BEKO-CAT is fully controlled. And it's always better than class 1. There's not more to talk about that. But there is still one negative point, and that's the invest. So the invest is for sure dramatically higher than the treatment processes with activated carbon. We will show some examples with numbers also. But finally, you cannot BEKO-CAT sell by price. This is not possible. But compared to oil-free compressors, it's far cheaper. We will also look on an example what's the difference between oil-free compressor and lubricated plus BEKO-CAT. So there's just the invest, which is on the negative side. So to sum up this, the BEKO-CAT is one of the answers that BEKO have to oil-free treatment systems. And the BEKO-CAT is available in sizes from CC10 to CC705 for the US market, and CC18 to 1200 for the other markets. And on the other hand, we have the activated carbon tower ClearPoint V. This is also in a certain range of sizes available. Here, the small sizes, the S and the M types, they look the same as the filters here, and they have integrated cartridges. That's for the S and the M versions. The bigger types, V100 or V2800, respectively, the L205 and L8200, these are tower versions with threaded or flange connections available. So how does the treatment process of the BEKOSPLIT looks like? For that purpose, I would first also recommend the videos we have on our Bautechnologies YouTube channel. This video very good describes the process of the BEKOSPLIT itself. But we will pick up the key component inside the BEKOSPLIT, and that's the chemical reaction. So the chemical reaction is taking place inside the tower, and it's supported by heat and catalyst, and the resulting chemical reaction is together with oxygen that we create a new molecular structure. So what do we have when the air comes into the BEKOSPLIT? We have the hydrocarbons, so the certain amount of C atoms and hydrogen atoms which are creating the hydrocarbon molecule. So that's the oil vapor that enters the system. And also, of course, there's oxygen in the compressed air because this is sucked in from the ambient. And together with oxygen, heat and catalyst, these hydrocarbon chains are cracked down to single components, and due to the chemical reaction, they result in new molecular components such as water and carbon dioxide. So the carbon dioxide is, just from the name and from the component, one negative effect we do not want to have in our environmental condition. But there are no worries in that situation, because the source where these carbon dioxide is being created is only based on the amount of oil which is entering the treatment system. Yeah, and you may know that the amount of oil vapor is approximately 1,000 times less than the amount of water vapor which enters the compressed air system. So, but we will also see a bit more numbers on a couple of slides later. So, as already mentioned, the process is temperature controlled, and each BEKOSPLIT has inlet and outlet valves. And these valves will be activated if the limits of the temperatures will be exceeded. That means that there is no more air for the production. For some people that sounds worse, but the good point is that there is no risk of oil contamination for the production. And if there is, for example, a 24/7 operation on customer side, then it's very important to be considered that any treatment system where the BEKOSPLIT is included needs a redundancy or at least a functional bypass system. By the way, I would recommend to do that all the time, to integrate any functional bypass system, because in terms of maintenance, you are more flexible, or the customer is more flexible, not to interrupt his production. All right, that's so far about the BEKOSPLIT itself. So at the next slide, we will see how the clear-bond V is working, how the adsorption process works. And that is, let's say, this is influenced by several parameters you see here in the circle. One point is the van der Waals force. So Mr. van der Waals, that was a Dutch physician, and he discovers this force. And this force is kind of small attraction between two components on the surface of one component to the surface of another component. This small attraction works on molecular level. So it has a quite low level of attention. The next point is the capillary action. Capillary action appears in the high porous of the activated carbon in the very thin channels which are at the inner areas of the activated carbon. And this force is independent from gravity. You may know this from very thin straws, where water is rising up in the straw, although the gravity should that pull down. The next point is the mass transfer. Mass transfer means that mass is being transferred from one component to another. In our case, for example, it's the oil vapor mass of oil vapor which is being transferred from the compressed air stream into the activated carbon. And last but not least, it's the partial pressure difference. That is, you could say that's the key word, why that process anyhow works. The partial pressure difference is the driving force to move the mass. And in that scenario of oil vapor treatment, this force is very small because the difference of partial pressure of oil vapor in the airstream compared to the amount of what is in the activated carbon is very small. There's not such a big gap as it is in a desiccant dryer, for example. That is far more easy, this adsorption process, because there's a big partial pressure difference, which is not given here. And that is why this adsorption process of oil vapor is very sensitive. And it can negatively be influenced very easy due to these fluctuating operating conditions. So let's have a short look to an example. What does mean the huge gap between the residual water vapor and residual oil vapor? For that, I've prepared one slide here to let you imagine that this space, let's say that space is the area of 35 cubic feet or 1 cubic meter. And you will see now some smaller square fields. And these square fields that will appear here in a few seconds, they stand for the space that corresponds to the residual water vapor content after different types of dryer. So that's, for example, the space of water vapor compared to the 35 cubic feet after the fridge dryer. And the next type of dryer is the desiccant dryer, and that's, for example, the amount of water vapor after a PDP of minus 40 degrees. And in between both of these, we have also a factor of 50. So the water vapor at desiccant dryer is 50 times less than that from fridge dryers. So comparing this to the residual oil vapor load at class 1, that is to be defined here in that space. And the black dot in the middle of the bull's eye, or the black dot in the bull's eye here, that stands for the space of the oil vapor. So I can imagine that nobody of us is able to see the black dot in the white space here in the bull's eye. The reason is that that is such small, or that small, that you would only see it if you use a microscope. Because the load of oil vapor is far different to the load of water vapor. In numbers, with the same unit, we talk about this value here. And when talking about the regular unit we use for oil vapor, it corresponds to the 0.01 milligram. So easy to see that we are far away from the amount of water vapor, and that makes it probably a bit more easy to understand, and to understand that adsorption process of oil vapor is far more difficult than adsorption process of water vapor. So between a desiccant dryer water load and the oil vapor water load at class 1 is a factor of 10,000. And for me, it's a quite good help using that sketch to make it a bit more visible what's the difference in between these two processes. Yeah. By the way, I mean, there is no agenda break in between, but let just give you or me the chance to pick up some question or to answer some questions.
Yeah, Bernd, there are two of them actually, both regarding the BEKOCAT.
All right.
I remember the point where you showed the benefits of the BEKOCAT, or the positive points, and one of them was it is load independent. And I also remember that you said that it can go down to 20% of the nominal volume flow, so minimum 20% of the nominal volume flow that it can work. So the question now is, does it need constant volume flow, or is volume flow with fast changes also possible? So without constant volume flow and fast changes, would it still work?
Yes, absolutely correct. So it's definitely independent, no matter if I have a constant low flow or if I have a fluctuating airflow. That's also know by experience that there's no problem with the function of the BEKO-CAD in that purpose.
Yeah, I mean, we see that daily in our showroom, I guess.
Right.
So that works completely fine. Okay, thank you for that. And the second question was, even though it's a little bit more market related, what is our typical target market with the BEKO-CAD? Maybe you can give short, say some words about this.
Yeah, I wouldn't say there is a target market. Probably it's it's all these companies which has where the requirement of high quality of compressed air is set on a high level. This is particularly mostly true for automotive industry when it comes to these surface technology areas, for the painting areas, for example, for chemical and pharmaceutical industries, and in many cases, not in most cases, in the food industry, because some people may wonder, but in fact the food industry is a bit behind the others related to the requirements of air quality. That is a bit surprisingly, because food is one important issue that we take daily. Yeah, but the quality requirements in the food industry are not as high as in some other industries. But by the years, following the years, they are begin to be more sensitive, because troubles in the market that some foods are being detected with some oil result in a worse reputation for these companies. So they become more and more sensitive for this topic. Yeah, I think it's not easy to answer this question.
Yeah.
What is the market which is good for the BEKO-CAD? Generally, I would say it's mostly it's a type of customer or the type of company that sets priority to process safety, and that's the major keyword. Yeah, the process safety. If that's the most important factor for this company, also in terms of air quality, then it comes down to BEKO-CAD.
Yeah. I think that last part sums it up perfectly. There is no typical target market. If process safety is the highest priority and no contamination of the end product, then you need BEKO-CAD. Okay, then this was the question so far. Thank you, Bernd. Go on, please.
Okay, thanks very much. Let's go ahead. So after this example, I would like shortly to show what the processes looks like and what is the influence of the processes, the two different ones. Let's start with the example of adsorption with activated carbon. So we picked up these four parameters: the oil vapor and pressure on the left scale, and the temperature and the dew point on the right scaling. And the curves now popping up here shows what happens with these parameters when they pass the activated carbon tower. So the oil vapor, for sure, will be reduced, because that's part of the process and that's the goal of this process. Also, the PDP will get slightly lower, because what has already communicated is that the adsorption process does not decide whether it should adsorb oil or water vapor. The temperature will slightly increase due to the exothermal process where the adsorption is based on, and it's not as high as it is in desiccant dryers, but we will have a slightly increase of temperature here. And finally, there is pressure drop, which is always given in any treatment component, because the flow resistant appears here, and that's the reason for the pressure drop. That's so far for the activated carbon tower. How does it look like at the BEKO-CAD itself? It's a bit different, particularly about the oil vapor content. It's always in the very low level compared to the inlet conditions, and no matter of inlet conditions. That's also an important point. The dew point mostly increases. Why do I say mostly? Because there is no yeah, there's no adsorption material. It's a catalyst material integrated, and that is the supporting material to support the chemical reaction. But anyhow, this catalyst material is also a kind of porous granulate. And this porous granulate has the property to somehow collect the oil-water vapor. I would not say adsorb. You could say adsorb because it's also easy to reverse. So it somehow collect the water vapor, and after a period of time, it will release the water vapor. And that's the reason, one of the reasons why we have an increase of PDP. One other is based on the chemical reaction. We have seen that already, that because of cracking hydrocarbon with oxygen into water, into H2O, we have also an increase of the relative humidity and the PDP at the outlet, particularly of the PDP. But the same as before with the carbon dioxide, it's not a big issue because the source to create more water is only coming from the amount of oil, which is always just in microgram and not in milligram. But as I said, in some cases the PDP will also get lower. This is based to the collecting property of the catalyst, and this is always a fluctuating result. So once you have a kind of BEKO installed in your system, and you have, for example, somewhere a fridge dryer installed, and then the BEKO, and at the outlet of the BEKO, you will easily identify that you have a fluctuating dew point. The same scenario will be if there is desiccant dryer somewhere in your compressor room, and the BEKO is at point of use. You will also have a fluctuating PDP after the BEKO. So that means, in any case, if there is a constant low dew point required for the oil-free application, you need an additional dryer after the BEKO. There's no question about that. So what about temperature? Of course, because there is a heating system integrated, and also the chemical reaction is an exothermal process that will all impact the increase of temperature. The BEKO has an integrated heat exchanger, but that's an air-to-air heat exchanger, and due to the physics of this heat exchanger, you cannot avoid that there's a temperature increase at the outlet. And the approximately difference between inlet and outlet is something about 5 to 15 Kelvin. That depends on the amount of flow, on the speed of flow, and on the size of BEKO. But it's a point that needs to be considered for further treatment components. Also, the pressure drop is occurring here, and that pressure drop is on a bit higher level than compared to the activated carbon. In numbers, we talk here about 3.6 to 8.7 psi, or 0.3 to 0.6 bar. And on the next slide, we will also have a comparison of both, and I will also pick up on some reasons for that. So the biggest gap here is the PDP. I mean, beside the oil vapor gap, it's the PDP that lowers automatically at adsorption processes, but here it will fluctuate. So the other point we realize is that the pressure drop is on a bit higher level. The reason is that this BEKO has integrated a few more components than the carbon tower. So we have the tower here, we have the heat exchanger, we have the piping in between, and the inlet and outlet valves. So all these components have an additional influence of pressure drop. All right, so that is the comparison of the processes in terms of the parameters. On the next slide, I would like to show you a table that comes up with a few more numbers. And these numbers show different, are focusing on different topics. That's, for example, here the performance area, where you can figure out what's the possible volume flow, what's the pressure and temperature. And you can easily see, for example, that the clear point V is available for a higher volume flow than the BEKO, which does not mean that's the end of the story. You can also integrate several BEKO-CAD in parallel installation. That's what we have also done, particularly in automotive industry, where they have a high demand on airflow. Yeah, pressure is different slightly. Temperature is almost equal. What is very different is the inlet dew point. We already talked about that. The operating costs are different because the BEKO-CAD is power supplied. And the major difference, what I would say, is the process safety. That fits back to the question that appears during the break in the chat room. The process safety is one of the key words when talking with customer to convince them to integrate BEKO-CAD in his system. So on the next slides, we will concentrate a bit more on these two areas here, on the invest and the process safety. And for that, we have prepared one table here, one table sheet. At the moment, this graph is only true for the European market, which is based to the price difference of BEKO-CAD between Europe and the US market. However, we will see a few graphs that will demonstrate the difference of the total cost of ownership. So the assumption here is that we will have a yearly replacement of activated carbon and the filters at clear point V. And so you will now see one gray and one yellow graph. The difference here is that the yellow one has the filters already integrated, which requires a yearly exchange of the filters. That's the difference between these two ones. And if you put in the biggest BEKO-CAD size here, the CC1200, that is the total cost of ownership of about 30,000 euros. So why is that just a horizontal line? So the assumption here is that we do not have any maintenance for the catalytic converter. And assuming that, we still do not have any matching point after 12 years. And that is one point that we, particularly as salespeople, we should realize that there is no return on invest with BEKO-CAD. That does not exist. Yeah, not in terms if we compare it to any treatment system, such as activated carbon. If we compare that to compressors, that's another story. We will also have examples for that. But here, the price is fully different, the invest is far lower, and also the total cost of ownership is continuously on a higher level than to the other treatment systems. So let's make an example with a complex compressed air system. What we see here is a regular system starting with the compressor, water separator, and receiver. And then we have two options of treatment processes. On the upper line, we have the adsorption line, let's say that way. On the bottom line, we have the chemical reaction line. The example is given us a few numbers of the airflow consumption, of the operating pressure, of compressed air temperature, and of required quality class. And we will concentrate on this area of the relevant treatment components. And following the numbers here from the example, we will end up with a certain type of models here. So that's for the US and for the European market, the different types of desiccant dryers here. And the towers have also a different model type. So these two together result in a kind of invest. This is quite similar, so it's almost 30,000 euros or dollars that you need to pay for this treatment installation. So on the bottom line, where the chemical reaction takes place, we have also the integrated models selected. And now we have a bit higher difference between the US and the European market, which is related to the different price of BEKO-CAD in the two markets. So these are resulting numbers for this installation. and you will end up to 3 times higher invest, or even to a 2 times higher invest compared to the treatment system with adsorption process. So again here, yeah, the information given by this slide or this exercise is that you cannot sell the BEKO-CAD by price. It's definitely not possible. It's not competible, and there are other ways to convince people why this is a reasonable product for your production, because it's always better than class 1 and it gives you the highest process safety. And this performance of the BEKO-CAD is also proved by certification. So we have two of these. One certifies the performance of the BEKO-CAD, which is given here already, and the other certifies that after the treatment of BEKO-CAD, there are no more bacteria in the compressed air system. That does not automatically mean that I do not need sterile filtration, but it will in fact increase the lifetime of sterile filters, because there are almost no germs entering the sterile filtration system. On the way between BEKO-CAD treatment system and sterile application process, probably there are some pipe connections, valves or whatever, and these are risky areas where some germs, bacteria can enter the systems again. But from the compressed air stream, all these bacteria are eliminated by the function of the chemical reaction and the heat inside the BEKO-CAD. So another positive argument for the process safety. All right, so that's so far about the portable processes. Any questions so far at the moment, before we start with the oil-free and lubricated comparison?
Yeah, there are 3 of them left. One is a question that tells us that an oil content of class 1 was measured downstream in ever-dry adsorption dryer, but without any oil-free treatments or no clear point B or BEKO-CAD installed. So the question was, is this normal?
Yeah, one question from my side: was it a lubricated or an oil-free compressor? Was that mentioned in the question?
It was not mentioned. I guess we find out afterwards, yeah. But so far it was not mentioned.
Mm-hmm. I mean, in fact, the desiccant material, so the adsorption material, which is responsible in desiccant dryers to adsorb water vapor, also adsorbs oil vapor. But it's unnecessarily polluted with oil vapor if I have, for example, no BEKO-CAD in between.
It was an oil lubricated compressor just in between.
Okay, an oil lubricated compressor. Yeah, it's a bit surprisingly that that was measured. Question is, how was it measured? Was it measured with the OCV?
OCV.
Okay, it was measured with OCV. So it's definitely an online measurement, and yeah, it's a bit surprisingly. I think I heard about that scenario, that there was one measurement done after ever-dry, but I wasn't sure if that was lubricated or oil-free compressor. I have no answer, no correct answer on that. What I can only explain is that somehow the oil vapor is also being adsorbed within the desiccant. If that works for long term, it's something I cannot promise and I cannot explain, but it definitely occurs. But I would not rely on such system only with the adsorbent in desiccant dryers, because these adsorbent has different properties than activated carbon. So the adsorbents in desiccants are either molecular sieve or activated alumina or silicon gel. And these adsorbents are manufactured with properties to adsorb water vapor as good as they can. The side effect is that they also adsorb oil vapor, but probably not in long term. And I would not rely on such a system without any further treatment.
Yeah, I guess that's a good point. Mm-hmm. Another question was, is the air exiting the BEKO-CAD fully saturated, so at 100% relative humidity?
Mostly, so let's say you have that BEKO directly installed after the compressor, then of course 100% saturated compressed air will enter the BEKO. We add some more water molecules into the system, but we will also increase the temperature at the outlet. So in fact, the relative humidity in most cases will be lower than 100%. Because the relative humidity is related to the temperature and not to the dew point. Another point is the dew point will get worse because of a bit higher water load at the outlet, but not the relative humidity.
Okay, and also one question: what does it mean that there were no fixed service costs mentioned for the BEKO? Does it mean that there is no existing maintenance plan?
Yeah, that's a good point, because I already had a chat with the product manager regarding this this topic. What is described here is that for many years there are almost no components that needs to be exchanged. Particularly the catalyst does not to be exchanged in the first 5 years. What needs to be done in maintenance is that I need to check some safety components. I need to check the in and outlet valves. I need to check the activation valves of these in and outlet valves, and I need to change the safety valve. But that is quite a cheap component, and that was not integrated. So in fact, there is maintenance required for the BEKO, but for many years on a quite low level, and only after 5 years the exchange of the catalyst is required, which is the biggest price consuming maintenance in this period.
Okay. There was only one information mentioned that, I mean, you talked about the effect of the BEKO and the water, that we maybe need a bigger dryer downstream to BEKO because of the rise in temperature of the BEKO. So, of course, I guess, yes, it depends on what this rise on temperature means or what bigger dryer means. But maybe just as an answer, of course, you could also just install a cooler after the BEKO and then you don't need a bigger dryer. Okay.
Absolutely true. Absolutely true. If it comes to the edge of performance of one type of dryer, it's definitely recommended to use a bigger one or to cool down the compressed air in between. Absolutely true. Yeah.
Exactly. Okay, that was it so far. Then please go on.
All right.
With the rest of the presentation.
Yeah. Regarding the time, I see that there's not so much space for me. So we have almost 15 minutes left. I hope that we will end up in time. Probably it may take a few minutes later, so please be prepared that I'm probably not finished at the end of the 90 minutes. Just an excuse beforehand. So the next part would be the oil-free or oil-lubricated plus treatment system. So this comparison, what does it mean? So the following numbers that we will see here are based not only on brochures, but on technical information from a compressor manufacturer. So the graph shows the specific power consumption for two-stage oil-free compressor. In this case, 7.29 kilowatt per cubic meters per minute. Compared to this, the lubricated screw consumes a lower amount of specific power, and we added to the lubricated screw the BEKO that consumes a certain amount of specific power, and the BEKO creates a pressure drop that results also in an additional power consumption. But easy to see that there's still space open, and that's the space where we have a saving potential of the BEKO of approximately 7,500 euros per year regarding energy consumption. And compared to this, on the other side, we have also the question about investment costs. So how does these look like? For that point, I picked up the two scenarios, the cost for the European market and the cost for the US market. So that's some regular price for an oil-free screw compressor. By the way, I hope you see that on the slide before. This size of compressor is somehow related to 55 or 75 kilowatt. And so compared here to the oil-free compressor, we have the invest of the lubricated screw, which is less than half of the price, or almost 1/3 of the price of the oil-free screw. Then we added the price for the BEKOSPLIT in euros here. And that's also far because there are no running costs. It's just we talk about invest. And the residual space is the saving potential in invest for the BEKOSPLIT, which is almost 30,000 euros. So if the customer would like, he can buy a second lubricated screw for the saving potential for another application in his company, for example. For the US market, because of the higher price of BEKOSPLIT, we end to a slightly different story. We assume that the compressors has the same price there, but the BEKOSPLIT is far more expensive. But even here, we have a saving potential of almost $9,000 in invest. And that's the one point where it becomes interesting maybe for the customer if he compares his oil-free compressor with lubricated ones. And it's not only the invest. In many cases or many companies, they start somehow with a regular application, with a production area where a regular compressed air quality is required, let's say the 242 quality class. And later on, they build up a new premises where an application is integrated that requires an oil-free compressed air quality. So he can still leave the lubricated compressor there if it's big enough from the airflow. He can just add the BEKOSPLIT on site of the new premises and has a point of use treatment for his brand new application. That is also just an example to be considered. So when we talk about these treatment system, let's pick up two different examples. So one is that we have a typical, so let's say a low budget solution for an oil-free compressed air system. All the components after the oil-free treatment needs to be oil and grease free. And the points here that this system is load dependent, as already mentioned, because we're running activated carbon tower. It has low or almost no process safety. And it's good for class 2 because here that's the combination of fridge dryer and activated carbon. If this is a combination with adsorption dryer, then it would also work for class 1. There's no question, of course. The other option we have is the oil-free treatment system with a catalytic converter. And also here, all the components after the oil-free treatment needs to be oil and grease free. And this is, as already mentioned, load independent, has highest process safety, and guarantees class 1 always. Let's go a bit more down to the two different scenarios of compressed air treatment at the central compressor station or at point of use. So let's start with this example here. We start again with the compressor with the BEKOSPLIT, and here, for example, there's also the cooler integrated between BEKOSPLIT and desiccant dryer. This is related to the higher outlet temperature. So you always should consider the conditions on site. When there's good ventilation and an average low temperature in the ambient, you may not need this additional cooler. But if you are in an area where the outdoor temperature is regularly on a higher level, that's probably helps to lower the size of the desiccant dryer, because probably the additional cooler is cheaper than the bigger size of desiccant dryer. So these installation will end up in the same qualities of various type of applications, and that's the central treatment at compressor station. All these components needs to be oil and grease free. That should be, or that has to be considered in any type of maintenance and additional integrated installation. On the other hand, we have, as I said, a typical standard application or standard installation where we start with the compressor, water separator, filters, fridge dryer, and an additional filter and the receiver. So that's then the way to the application, and that is finally the workshop quality, let's say that way, the 242 class, which is very common in the industry. So this customer has later on integrated an application that requires oil-free air, and so he added just the BEKO on site at the central treatment process at the point of use. I just ignored the quality of humidity here of the PDP because that depends on the customer, whether he needs a lower dew point for his application or a fridge dew point. But anyhow, in any case, an additional dryer should be integrated after the BEKO cut. Otherwise, you will have a fluctuating dew point where you have no idea in what range of value that will appear. And one big advantage here is that we only need to put in all components oil and grease free in the far smaller area compared to the upper installation here. Yeah, so that reduces the cost of new piping, for example, and reduces also the cost for the regular maintenance. But it's something that can only be clarified and identified on site, and there is no general rule, of course. It always depends from the customer on site. All right, that has been just a few slides because we are now at the last point. Are there any questions before we go to the measurement technology?
Actually, yes, there is one question. You were showing the prices for BEKO, and there is the question why the difference in price between Europe and USA is so big. Of course, there are import costs, but still it seems a little bit high. So have you any information about
No, I didn't get the information so far, so I didn't ask the colleagues in the US subsidiary why that is the price. I pick up the price from their price book, which was from 2018, and I have no further idea. Maybe we can later on give an answer to that question after the session.
Okay, something to clarify later, yes, no problem.
Yes, sure.
There's one point, there's no need of using a pre-filter upstream the BEKO, there's only water separator on the picture, is that correct?
Yes, in that installation it is correct, because the water separator is good enough to avoid any droplets entering the system, and in that case it's okay for the BEKO. I wouldn't say that is a general recommendation. Please always have a look on the suction conditions on site. If that is, for example, an area where frequently a huge amount of dust will appear, I would also recommend to put an additional filter. Yeah, but then a coarse filter, so a 25 micron filter would be good enough, I would say. Some people may recommend a different quality class of filter, but that would be okay.
Okay, just one last question. Right. Is there any other way in judging or determining the life of the catalyst besides using an OCV and checking the oil content if it is still okay?
Yeah, wait until you have oil into your production. That's a silly answer. There's no other way. I mean, the OCV would be the best option in that case, and it gives you, in the shortest period of time, will give you an information what happens and when is the lifetime of the catalyst exceeded. And if you do not have this OCV, the only chance to put regularly samples and send it to a laboratory and wait until you get the numbers.
Okay, and one last one just dropped in. Will the use of a pre-filter extend the catalyst lifetime?
I wouldn't say it will extend the catalyst lifetime, but probably it will guarantee for a longer time that the pressure drop inside the catalyst tower will not increase, because it's easy to exchange the inlet filter regularly, but you cannot change the catalyst every year because the pressure drop will increase. Pressure drop may increase because of particles will enter the system, and when particles enter the system and are collected in the catalyst tower, they will reduce the open space for the airflow, and that will result in a higher pressure drop. So from that point of view, it would be recommended to place an additional filter upstream to reduce the risk of increasing pressure drop. But then,
so the particles will actually not have an influence on the actual lifetime of the catalyst, but on the function of the product in general.
No, it will not influence negatively the lifetime of the catalyst. But the pressure drop is the key word in that case.
Exactly. Okay, then maybe just finish the presentation, I would say.
Okay, cool. Yeah, hopefully if most of you will have just, let's say, 10 minutes time, then we should end up the story here. Last point is, how can I be sure? One should ask the customer if he knows the quality of his compressed air and that he does not forget to measure. So what measurement equipment is reasonable to put in such a air system which is on a high quality level? So we have, for example, the dew point sensor, the pressure sensor, and the oil vapor measurement equipment. And these three measurement components are mostly related to quality issues. Another sensor is the flow meter, and the flow meter is mostly integrated regarding cost estimation. All of these sensors can be connected to a data logger, in our case the Medmon BDL data logger, to record all the data, and these data can also be transferred from the data logger to a customer PLC, for example, either via Modbus connection, and it can also be displayed on the web server, for example, where the customer can also see these numbers on a browser surface. Additionally, beside these sensors that uses an extra display at the data logger, we have also a local display that enables the customer to read data on site. And this local display is adaptable to the analog versions of the pressure sensor and the dew point sensor. So the question now is how to integrate these sensors into the customer compressed air system. So we have now a variety of collection of all these sensors, and we now go to the customer, visit his premises, and are facing that scenario here. So this is a building with separated areas. On the basement area, we have the compressor station. And this compressor station is mostly interested for us as sales and service people, because we need to be aware that all the products function properly and that the required quality is being created here in that compressor room. On the upper floor is the area which is most important for the customer. The black boxes here are just displaying different applications. And we have two application areas separated by the two rooms. And that is the area where we should start to integrate the measurement equipment for the customer, because that is what the customer is focusing. He's in fact, almost any customer is not interested in what happens in the compressor room, because he is interested that his production works properly fine and that his product is manufactured in a high quality. So let's start to put in some sensors here. What's reasonable at first is the dew point sensors, separately for each area. And the dew point as well as the pressure sensors are a good indication for the quality of the air in terms of pressure. So why the pressure? In some cases, for example, the pressure is relevant for the performance of tools. Screwdrivers, for example, need a certain kind of pressure to create a torque which is required to turn the screw into any assembling situation. Dew point could be relevant if there is, for example, a gluing application or laser cutting machines are running. So dew point is in fact a quality number that needs to be considered. Furthermore, if that's oil-free applications, additional Medpoint OCV should be integrated to get aware of this quality in terms of oil vapor. So these are so far the quality issues for the application area. In many cases, the customer is also interested in the amount of costs which are created by the numbers of application. And these costs should be separated for each application. So all application would get a flow meter integrated. That's for the customer, it is easy to detect the costs for his application which is created by the compressed air consumption. So both areas for sure needs a data logger where all the sensors are integrated to, and these data loggers can be read out either on-site or they are integrated to the customer network or they are transferring data via Modbus to his PLC. So there are many options where the customer can take out these data. That's so far done for the customer area, and now we need to go down to the compressor room in the basement, so let's say, and there are sensors to be integrated, which is important for us. Mainly important because in terms of service and particularly in terms of troubleshooting. So we need to be aware, when I say we, that we as BEKO sales and service people or our dealers with service needs to be aware of what happens on site. And for that purpose, at first, we can integrate pressure sensors. And why the three pressure sensors? That's easy to explain. One simple pressure sensor at the outlet of the compressor. It's regularly recommended to see what's the outlet pressure of the compressor. A second pressure sensor after the vessel, and the third one after the desiccant dryer. And in a combination of the data logger and so-called virtual channel settings in the data logger, we can also easily identify the pressure drop around the desiccant dryer and the pressure drop around the BEKO cut, which is an indicator for preventive maintenance, for example, or to show, to realize that some particles are collected and on a higher level and so on. So that's the reason why we put in these pressure sensors. But we also need to know what's the dew point and the flow. Particularly, the flow is a very helpful tool in terms of troubleshooting, which is related to dew point. Imagine the desiccant dryer somewhen does not give you the required dew point. So we need to figure out what's the reason. So the reason could be end of lifetime of desiccant, but the reason could also that somewhere in the application area, additional application has been integrated. And for example, the compressor and the BEKO cut can stand this higher demand of airflow, but the desiccant dryer was already selected on the edge, and now it is overloaded, and it will not give you the required dew point. And the flow meter here installed will give you automatically a good number to figure out what was going on. Yes, so finally, also here, a data logger should be integrated. And this data logger will give you automatically a recording of these detected values. And you can also pick up these data from the data logger if you have access to a customer network, for example. So far, that's the integration of some measurement equipment in terms of quality issues and of cost estimation here on customers area, and for performance and troubleshooting issues in the compressor station. All right. Finally, I would like to give you just 5 tips to be successful in your daily job. So one point is ask your customer. Ask your customer what's the quality standard the company needs to follow. And a very good question is also what is the compressed air used for? You may wonder or I quite often wonder when I ask our salespeople when they come back to us and explain some installation on site, and I ask them, so what is the compressed air used for? And many of them has no idea. But the customer would feel more happy if you will be interested in his application, because that is the best source to figure out what is the required quality class. And does he have any pain points? Second step is record the status quo. it's definitely required on one hand, but it's also helpful. Yeah? Helpful to make sketches, to make photos if you're allowed to do some, and probably probably to make an air audit. Yeah, an air audit gives you numbers where you can start your recommendation. So always start from the application and go down to the compressor, as already said. Because the application is the most sensitive area for the customer. He is definitely not interested in the compressor room. Make your recommendations which are based on the recorded status quo, and these recommendations can follow different demands. It's either the quality demand, it's either the energy saving potential, it's the process safety which is interested. It's something you should figure out when you discuss with the customer what he is mostly focusing on and what is the priority in terms of improving his compressed air system. And finally, ask your customer again. So after everything is integrated, we should be interested what is the result after several time, after a couple of weeks or a couple of months. It depends on the size of the compressed air station that has been built up or has been integrated. It has two positive side effects. One is that we get more experience of how the situation looks like after a period of time. And the second side effect is that the customer feels more happy if we are continuously interested in the good quality of his application and in the good performance of the compressor station. And once the customer is happy, ask for a reference, because references are always to be used in sales job, and they very often help to be convince the customer and to be somehow successful. All right, so that's all for now. And from my point, please kindly apologize the little delay at the end of the story. And I hope you get a lot of information worthwhile for your job, and would be happy, as I said, to welcome you to our next webinar session. Thanks very much.